Okay, in this video we're going to be doing some application problems with exponents and logarithms. Really going to be focusing on using logarithms in order to solve problems that are applicable to exponentials. The first one that we'll do is just a regular exponential growth or decay problem. For example, let's say if you have a baseball card that you buy for, let's say you bought it for $15. So that would be the initial value of the card. Now, because of the player's performance, maybe the baseball card goes up in value every year by a certain percentage. So the value increases by, let's say, 30% each year. And what you can ask yourself is, when will the card be worth let's say $200? So what we want to do is we want to write an equation down that models this. So the general model is, for this kind of problem, would be A equals P parentheses 1 plus R raised to the T. Now what these values mean is T means the amount of time that you wait for something to increase in terms of value. R would be the interest. And you've got to make sure that you write it as a decimal. P is the initial value, and A would be the final value. So if we're going to model this, the final value will be $200. So we'll have 200 equals, P is the initial value, that was 15. Then we have 1 plus the rate of interest as a decimal. So 30% as a decimal is 0.3. So 1 plus 0.3 is going to be 1.3 raised to the t power. And it makes sense that we're going to be solving for t because we have the question when. Okay, so at this point what you want to do is you want to isolate the base to the power. So there's your base, there's your power. You want to isolate that. So what we're going to do is we're going to divide both sides by 15. So we're going to have 200 divided by 15, and that comes out to be 13 1/3. So 13.3 repeating equals 1.3 raised to the t power. Alright, at this point, now that you've gotten the base to the power isolated, you want to introduce logarithms and use the power rule. So ln 13.3 repeating equals t ln 1.3. So we're putting ln in front of the 1.3, and we're taking the t and we're using the power rule. So it's t times ln 1.3. So in order to solve for t, I would now divide both sides by the ln of 1.3. That will cancel here and here. So t is going to be roughly, if you put 13.3 repeating divided by ln of 1.3, you get roughly 9.87 years. You can do this on your calculator. Just one thing that you want to make sure to watch out for is that on the calculator, when you hit ln, it immediately does this, ln open parentheses. Now if you were to type in 13.3, let's say you do a few threes here, you need to close off that parentheses before you hit the division sign. Because if you don't close the parentheses and you do the division here, it's going to do 13.3 repeating divided by the ln of 1.3, and then it's going to take the natural log of that. We don't want that. So you have to close off that parentheses, then hit division, then hit ln again, and then it'll be 1.3, and you close that off again, and then hit execute or enter. Okay, so that's just a very basic run-of-the-mill exponential by a certain, an increase of a percentage per year. That exponential, and again I'll write it over here, a equals p, we did 1 plus the rate, but really it can be plus or minus the rate. If this value, which is called the growth factor or decay factor, if this value is less than 1, then it's a decay. It will decrease over time. If it's larger than 1, it's going to be a growth, just like what we did. So if something, let's say you buy a car and it depreciates by a certain percentage each year, depreciating would be going down in percentage, going down in value. It would be 1 minus the rate. I mean, that baseball card, the player could have performed really, really, really bad. So then that would mean that the value of the card would go down, so it would end up being 1 minus a certain percentage to bring the value, the factor, less than 1. So that's one kind of problem. This over here represents just a run-of-the-mill exponential growth or decay. Decay. I gotta. Alright, D-C-A-Y. That's it. Okay. Can't spell. Okay. Let's do another problem. Let's do one where we're investing money. Suppose you want to invest, let's say $20,000 at a bank that gives you an interest rate of, let's say, 1.52%, and they compound your interest monthly, which means 12 times a year. And you want to find out, when is it going to be worth say $50,000. Now if you notice, the questions that we're asking are when questions, so the time is an unknown. The reason why I'm doing that is because I'm showing application problems where you have to use logarithms in order to solve the problem. And the reason why the when indicates a logarithmic solution or a logarithmic method in order to solve it is because the t value, the t variable, is located in the exponent. And usually, unless you can establish the same base on both sides of the equation, usually you're going to need to use logarithms in order to solve an unknown that's in an exponent. Okay, so for these kinds of problems, we're going to be dealing with one or two different kinds of equations. the first equation looks a lot like the other one. It's A equals P times 1 plus the rate divided by the number of times a year it's compounded raised to the number of times a year it's compounded times the time. Or if it's compounded continuously, meaning not 12 times a year, but constantly, and it would that fact would be made known to you in the problem itself. So if it said that the bank compounds it continuously, then you would use this formula, A equals P E raised to the RT power. So we would be using a base of E here. So this is only for continuous compounding. Whereas this is compounded n times per year. Okay, so for this problem specifically, when is it worth 50,000? 50,000 is going to be our end result. The P, which stands for principal, is the initial value, which was 20,000. That's how much we invested, times 1 plus the rate as a decimal. Now you might say, well, this is a decimal right over here. Yes, but it's still written as a percent. So we would have to move that 2 places to the left. So it's no longer a percent. So 0.0152 over n, number of times a year, that would be 12, raised to the n, which is 12, t power. And if this was continuous, again, A would be 50,000, P would be 20,000, E is a constant. It's roughly 2.718 raised to the 0.0152 t power. So it's actually a little bit easier to do a problem where it's continuous than it would be over here. So the first thing you would do is you would find this value. Find out what that is. Or you could divide both sides by that value. And in fact, that's what we'll do. So if we divide both sides by 20,000 to get rid of it on the right side, it would be 5/2 or 2.5. So 2.5 equals. Now I'm just going to find out what this equals. So if we take 0.0152 and divide it by 12 and then add 1 to it, you get approximately 1.00127. And again, you can do this on the calculator while you're watching the video or taking notes. And if you need time to work it out on your calculator, I would pause the video and do that as we're working through it. It's really important that you are comfortable with entering this information in the calculator and getting the right values. Okay, so just like the other problem, we've isolated the base to the power. Whenever we've isolated it, we want to introduce logarithms and use the power rule. So we're going to have ln 2.5 equals. Now when I use the power rule, I'm going to move the 12t in front of the ln of that parentheses. Okay, now we solve for t. So I'm going to divide by 12 ln of that value on both sides. So essentially I'm dividing by everything other than that t value. And you'll see that the 12 will cancel with the 12, the ln will cancel with that ln. So ln of 2.5 is roughly 0.91629. We're going to divide that by 12 times ln of 1.00127. That's roughly 0.01523. So if we divide those out, 629 divided by 0.01523, t is going to be roughly 60.16 years. It's a long time to wait, but that's the answer. Okay, let's do one more, and this one is going to be what's called a logistic model. So let's say I gave you a situation where there was a spread of a virus, or like a flu, or H1N1, whatever virus you want. There's a spread of it, and it's modeled by a particular equation. Let's say that that equation is f of t equals, let's say, 20,000 divided by 1 plus 162e to the negative 0.7 t. Okay, there's not many variables here actually, because e is a constant. T is actually going to be the number of weeks, let's say, after the outbreak of the sickness. So when t is 0, that would actually be the initial outbreak, like right when it started. So if we wanted to find out how many people were initially infected, all we would have to do is make t 0, and that would give us the number of people initially infected. F of t represents the number of people infected after a certain time t, or after a certain number of weeks t. So if the question is, when will there be, let's say, 9,000 people infected. So 9,000 is representative of f of t. It's the value after a certain time, and we don't know that time. That's what we're going to find out. So we would have 9,000 equals 20,000 divided by 1 plus 162 e to the negative 0.7 t. So we only have one variable, and that would be t there. So we need to find out what t is. The easiest thing to do first is to actually interchange this 9,000 and this denominator. And the reason why we can do that is because if I were to multiply both sides by this denominator and then divide both sides by 9,000, you would have that. So if we want to write all that out, what we can do is we can multiply both sides by 1 plus 162e to the negative 0.7 t. When I multiply the right side by it, it cancels. When I multiply the left side by it, it's going to be 1 plus 162e to the negative 0.7 t times 9,000 equals 20,000. So again, it's on the left side here because we're multiplying both sides by that denominator. So it cancels on the right, but it's going to be multiplied by 9,000 on the left. So now we want to divide both sides by 9,000. And that cancels 9,000 on the left. What we're working toward is this e to this power, because that's the base, that's the power. You want to isolate that, and then you can take the logarithm of both sides and then work with it that way. So we're going to have 1 plus 162 e to the negative 0.7 t equals, so 20,000 divided by 9,000 is going to be 2.2 repeating, or 29ths. Okay, now we're still working on trying to get this alone. So what we would do now is subtract 1 from both sides. So we would have 162e to the negative 0.7t equals 1.2 repeating. Now you want to get rid of the 162 by dividing both sides by 162. That will cancel it on the left. So we have e to the negative 0.7t equals 1.2 repeating divided by 162 is approximately 0.0075446. Okay, we've isolated this base to this power. Once you've gotten that done, you want to introduce ln on both sides and use the power rule. So I'll just put the ln here and here and just show you that if I were to take this and use the power rule and put it in front, we're going to have ln all by itself. ln is 1, so that's going to just cancel out. ln gone. So negative 0.7t equals ln of 0.0075446. Now to get t, it's pretty simple. You just divide both sides by negative 0.7. That cancels, that cancels. So t is going to be approximately ln of 0.0075446. Close off that parentheses. That's going to be important. Divided by negative 0.7. You get 6.98. Remember, t was weeks this time around. So really, really, really close to 7 weeks for this problem. And that's it. So in general, all of these problems, yeah, they all have different equations, but the equations, when you look at them, you really want to isolate the base to the power. Once that's isolated, you want to introduce logarithms on both sides of the equation, use the power rule, and then solve for the unknown. And in all of these cases over here, they're all going to be time. And that's it.